So today we are going to be talking about how we use efficient transparent checkpointing for AI workloads and in Kubernetes. And this work is a collaboration between my supervisors, Professor Rodrigo Bruno and Professor Wes Armour, and a few people from NVIDIA and AMD. Victoria, over to you.
Hi. So, do you know what all these talks have in common? So, during past KubeCons, folks have already presented some problems regarding inefficient resource utilization and fault tolerance. These people were worried and concerned about ensuring that GPUs are used efficiently and that any problems that arise concerning GPU are resolved simply because GPUs are an expensive resource. We can see that people from companies like Google, Microsoft, Huawei, NVIDIA, or CERN were invested in this, and they suggested various solutions, mostly using mix or time sharing, or some mentioned some new scheduling strategies. And the thing is that this problem persists, and in our case, we experience it too, but we are suggesting slightly different approach to solving these problems. So, who is we? I represent Czech National E-Infrastructure that operates multi-tenant, multi-purpose Kubernetes clusters that are free of charge for researchers and academics in Czech Republic. These clusters feature around 50 GPUs of various types and around 300 active users that operate different kinds of workloads that generally fall into two categories of batch workloads or interactive workloads. In operations, we aim for simplicity and some level of general applicability because of this variety of workloads, but also because by far not all users are proficient with containers, Kubernetes, or generally complex setups. Now I will present 3 insights from our infrastructure. So starting with the first one, on this graph, we can see the sad reality. So computational nodes seem generally occupied due to generous requests, but in reality, the real utilization is quite low. In this data utilization, in this CPU utilization graph, we can see computational nodes and their real utilization and the whole capacity. And the ratio between these two generally varies between 1 to 50%, with an average being 6%, which is quite sad and definitely could be improved. But overall, in cloud, some level of over-provisioning is necessary because cloud should be elastic, cloud should be able to provision for sudden spikes, and also cloud should be able to accommodate redundant workloads. And if this is the case with the CPU utilization, then we can imagine that with GPUs is sometimes worse. Continuing with the second insight, this insight comes from the category of batch workloads. So this plot shows AlphaFold jobs and their durations and the amount of jobs falling into the relevant duration category. AlphaFold is a protein structure prediction software, and jobs require a GPU to run, and they usually run for many hours, normally up to 10 hours, but we've experienced cases when a job ran for 30 days. Since it's a batch workload, GPU utilization is quite fine. It's usually about 90%. So the case is obviously fault tolerance. In everyday data center operations, hard or soft failures happen kind of all the time. So we want to ensure that these long-running jobs do not lose their progress. And so we would like to have some mechanism for ensuring their fault tolerance. The third insight is from the interactive workloads category. On this graph, we can see GPU utilization of a Jupyter notebook. We can see that it's quite unpredictable and dynamic, and there are times and bursts of activity followed by inactive periods, in some cases as long as 1 day. Jupyter notebooks, or generally interactive workloads, are expected to be readily available, but at the same time, we don't know when human will interact with them. And so, by definition, the resources are allocated, but can remain underutilized or not utilized at all. And it is worth noting that over-provisioning such underutilized workloads even worsens the problem of ineffective utilization. So based on these insights and also like the insights from the previous talks, we now can have kind of a wish list for GPU workloads with two wishes. First wish is a wish for fault tolerance, generally for any kind of workloads, but long-running workloads would be very interesting. And ensuring fault tolerance isn't essential, it's not a nice to have. Second wish is achieving efficient utilization of resources, mostly for interactive workloads, because we've seen what's their utilization pattern, and also because they're becoming more and more ubiquitous in the clusters. And of course, there exist some existing approaches to these problems concerning utilization, but not all approaches can be applied to every use case or to every workload. Over-provisioning is not suitable for all workload types because workloads need to be aware that they can be auto-scaled. Then GPU sharing in form of multi-instance GPUs is limited in up to how many parts you can partition the GPU and also can lead to fragmentation. Time sharing can worsen the performance and also is not suitable in environments where resources are shared by unrelated groups. New scheduling strategies tend to be workload specific and are not applicable widely in general environments. So we are suggesting to use another versatile tool and to have it in the toolbox alongside all these existing approaches, and that is transparent GPU checkpointing. And now to Radostin.
Thanks, Vicky. So as Victoria mentioned, transparent GPU checkpointing can be used for improving resource utilization or providing fault tolerance for GPU accelerated workloads. Last year at KubeCon, we had a talk presenting how we can enable coordinated checkpointing for distributed applications. And at the end of our talk, there were many questions about how can we actually checkpoint restore GPU applications. And this is a follow-up session on this talk. So there are a few existing approaches of how do we checkpoint restore GPU applications. And the most commonly used approach is to use something called API interception. So this is where essentially replacing the CUDA libraries or ROCm libraries, essentially GPU libraries with interception mechanism that works and replace API calls and keeps track of memory transfers. And the problem with this approach is it's difficult to implement. You have to essentially explicitly intercept every API call, and you have to track all the memory transfers. It adds performance overhead, and you have to handle the loading and essentially loading the kernels on the GPU, which is architecture specific, and it can be different for different versions of libraries. And it also requires dynamic linking. So for example, CUDA uses static linking by default for the CUDA runtime, so you have to recompile certain applications. And our approach is using recently introduced GPU capabilities that allow you to essentially checkpoint restore the state of GPU applications. We call this transparently unified CPU GPU snapshots because it allows you to create a single snapshot that combines both CPU and GPU state. It's fully transparent to the application. It works with both static and dynamic linking, and it's integrated into CRIU through plugin mechanisms. So this allows us to be used, for example, with Docker, Podman, other container engines, and Kubernetes. For AMD GPUs, the AMD GPU driver is part of the Linux kernel, and the AMD team essentially introduced new API calls, IOCTO API calls, that allow you to obtain information about the process currently running on the GPU and freeze the process from essentially evict the queues of the process. And the second step is to checkpoint the state of the process, which is saved into a file descriptor. And the unpause operation allows you to essentially unevict the queues. So these are the three main steps that can be used to enable GPU checkpointing. And similarly for the CUDA check, for NVIDIA GPUs, we have a few similar steps. The first is to obtain the status. Now, what is the current status of the CUDA task? To essentially pause the execution of the GPU process, and then to checkpoint the GPU state into host memory. And this functionality is exposed through command line utility called CUDA checkpoint. And there is a blog post on from Steven describing how this works in more detail. Integrating this functionality with Kubernetes is fairly simple. It's part of CRIU and it's fully transparent to the application. So it doesn't require, for example, to inject additional libraries into the container image or to essentially modify the workflow of the applications that are being used. And Adrian is going to describe in more detail how the checkpoint restore mechanisms work in Kubernetes. So we have a demo showing how we can use this mechanism for hot swapping of models. So in this case, we have the cluster that Viktória just presented using a single Kubernetes node running a training workload in a Jupyter notebook. And here we have high utilization, but we consider this to be a low priority task that will be running for a long time. And if we need to switch to, for example, high priority task, we can checkpoint the application from the GPU into host memory. And this essentially allows us to allocate the GPU to another process to essentially, in this case, use an inference workload with Llama 3.3. And this will essentially load the model into the GPU and start responding to the request. And if you have another workload with even higher priority, we can essentially checkpoint the inference task again into host memory. And then after this is checkpointed, we can essentially, we have two pods here. The first pod is a Jupyter notebook, and the second one is OpenWebUI, which serves two users. The first one is the Llama 3.3 workload. The second user is using DeepSeek. So the DeepSeek model has fewer parameters and it's faster. It generates a response in a faster way. And once the high priority workload, in this case DeepSeek, has completed, we can resume the execution of the inference workload, Llama. And once this is completed, we can also resume the training job at the end. So this transparent checkpointing mechanism allows to implement something we call hot swapping, essentially swap multiple models or workloads to and from host memory to essentially optimize resource utilization. And Adrian has another demo for migration later on. Just to show the evaluation results. So we evaluate the checkpoint restore mechanisms with different models and model sizes and GPUs, and we were able to demonstrate that it achieves transparent checkpointing for essentially faster recovery and to accelerate the cold start times of inference workloads. Adrian, over to you.
Yeah, thank you. So thank you for the presentation of the use cases and of the details about how it works with GPUs. I want to talk a bit more about the whole state of checkpoint restore in Kubernetes, focused on GPUs, but give some background around it. So I prepared another demo, a live demo. So we have seen the demo right now, which kind of preempts the running application on your GPU. And in my demo, I want to migrate an LLM from one host to another host while it's running. So here. So this is a really simple setup here. So this is Kubernetes and CRIU from Git, from maybe 3 weeks ago. I have this really simple pod definition here, which I will start now. And I have a Reber script around it, which tries to measure how long it takes for the application to start, so that we can see if maybe restarting from a checkpoint, and I hope it's faster, it should be faster, is actually faster than doing a cold start. So what's currently happening here is this is starting the VLLM. It's running on an NVIDIA GPU, an A10, on an Amazon EC2 something. It's a RHEL 9 based system, and it takes some time to start. It should be around 40 seconds, and then it should be ready to go. Yeah, so now the LLM is running. We can see it here. Oh, where's my demo? Here, NVIDIA SMI. So we see it's using around 4 GB of memory on the GPU. It's a Python process, and I can talk to my LLM using curl, and it basically I can just give it a sentence. CRIU is a Linux tool. So CRIU is the tool with just a checkpoint restore below everything. So I'm telling it, please finish the sentence. CRIU is a Linux tool, and the LLM says you should definitely try it out. I agree, and then it says a couple of things. So we have this container running in Kubernetes on our A10 GPU. And now I have a script which does the checkpointing. The checkpointing takes about 1 minute to write all the data to the local disk. The checkpointing interface in Kubernetes is currently a kubelet-only API. That's why the command line is a bit more complicated than just writing kubectl something. What the script will also do, it will checkpoint the container from the host and GPU, and then it will also transfer it to the second host. What's happening now here in the background is, so I talk to the kubelet talks to CRIU, the container engine talks to runc talks to CRIU, the tool doing the checkpoint restore tool, and runc, as Radostin mentioned, then talks to the CUDA checkpoint tool. The CUDA checkpoint tool will stop all running kernels on your GPU, will write all the information to main memory. Then CRIU will take all the information from main memory, make a stateful copy of your container, and then CRIU, the container engine, will add additional information about metadata and about file system changes. And all this information is then written to disk, and it takes about 1 minute and 4 seconds. And now this checkpoint image, which is quite large at this point, around 11 GB from the GPU and CPU side, is now transferred to the destination host. Currently in Kubernetes, this is independent if you use CRIU or containerd. They both create the same file format. It's a tar archive which contains all the information about your running process. If this is running with GPU or without GPU doesn't make any difference at this point. So now that the checkpoint image has been transferred to the destination system, I have to convert this to an OCI image. This is another script. This is basically running Builder in the background, which takes the OCI image, which takes the checkpoint archive and copies it which takes the tar archive and copies it into an OCI image. This will also take a couple of minutes, so I will switch back to the slides and go back to the talk. So the interesting thing is, if you look back in the history of checkpoint restore in Kubernetes, there's actually a ticket open since 2015, which talks about, it's a very high-level discussion about migrating workloads, migrating pods, containers. It doesn't go into many details, but the interesting thing from my point of view is that container migration has been discussed for over 10 years now in Kubernetes. And in 2020, we started working on this, and we put it under the story of forensic container checkpointing. There were a couple of reasons for doing it this way. Forensic container checkpointing, the idea is we have a container that's running, and you think it might be attacked or not. And what you usually did, or what tools today do, is they just kill the container and hope that your attacker can no longer access the system. With forensic container checkpointing, the idea is you can take a snapshot, a checkpoint of your container without a container ever knowing that it was checkpointed. and without knowing that your container was ever checkpointed. And then you can keep the container running, and then you can do an offline sandbox analysis of your container. If you just want to scan through all the memory pages, there's an option, or you can restart the container and see what it's doing, if it's doing something malicious or not. And the reason we did it this way, forensic container checkpointing in Kubernetes, is that the impact on the source code of Kubernetes was minimal if we just do the just do the checkpointing part. This is also why we today only have a kubelet-only API, just to minimize the code changes and see if this is a good idea to have in Kubernetes. In 2022, Kubernetes, with Kubernetes 1.25, the feature was released as an alpha feature, forensic container checkpointing. And since then, you can use it. In the beginning, it was a CRIU-only feature. And over the couple last 2 years, we worked with Containerd to get it also into Containerd. With Kubernetes 1.30, we switched the label, the flag of the feature from alpha to beta. The code changes to Kubernetes at this point in time were minimal. It was only about basically changing the label from alpha to beta. But at the same time, we also were able to get the changes into Containerd, so that Containerd also can do forensic container checkpointing, just like CRIU does. The interesting thing is I'm presenting here, and we're talking about also restoring containers. The thing what we did, or which we discovered in the process of implementing this into the container engine, is that we are able to restore a container without Kubernetes knowing that a container is restored. So when you start a container in Kubernetes, Kubernetes does a call to the container engine, container create and container start. And what we do in CRIU and Containerd today is we hook into container start and container create and start, and see if the image we passed is a checkpoint image. And if it's a checkpoint image, then we will restore the container. So from Kubernetes point of view, it's a new container, a new pod, but it's actually a restored container. This way, we today can implement container migration with or without GPUs in Kubernetes. Let's go back to our demo. So the image has been converted to an OCI image, and now I can start this container. So the YAML file looks almost the same. I'm putting another script around it to see how long it takes to start. And so what now is happening is now the kubelet will talk to CRIU, please create this container. CRIU will download the image from the registry, see, okay, we have information that this is a checkpoint image, we will unpack it, and tell runc and CRIU, the tools below, and CUDA checkpoint, please restore the container and do not create a new one. And this way we are able to do a stateful migration of the container without losing any information. And we see, so counter 6 is one of the examples that it's at the same point that it was here last time. So if we talk to it here again, we see counter 5, counter 6, and on the other host we see also counter 6, counter 7. Oh no, this is the wrong command. So this is the right command. So we see it continues from the same point it was checkpointed, but just on another host. And now we have 2 GPUs programs running from the same initialization on one host on 2 hosts. And it took a shorter time. It only took like 25 seconds instead of 40 seconds to start up. So even the startup was faster going from a pre-initialized GPU container. So back to the slides. The next steps we are thinking about, and we also discussed this with, I think, Signode. Yeah, Signode was it. Can we declare the checkpointing? Can we declare the checkpointing API as a stable in the kubelet? So basically finish the forensic container checkpointing feature, move it from beta to stable GA. And if this at some point will happen, maybe we can also think about integrating in kubectl. We opened a first Kubernetes enhancement proposal to extend the kubelet API endpoint for checkpointing to the API server. And once it's in the API server, we can also think about integrating in kubectl. this is an ongoing process currently, and it will probably take some time, but we're slowly trying to make it from the lower levels of Kubernetes to the upper levels of kubectl, so that it's easier to use than what I've currently shown you in my demo, reaching out directly to the kubelet API. Another thing I just saw last Friday, there's a company, Weaversoft, they released a tool for Kubernetes. It's a web interface which you can use to checkpoint and migrate container. I have not used it myself. It was just released on Friday, but I was very happy to see that. So that seems like people are, not just us three are interested in the topic. There are many more people looking into it currently. So with this, we are at the end of our presentation. So we mentioned that we are able to fully transparently checkpoint GPU applications. It works with AMD NVIDIA GPUs, and it's out of the box integrated in Kubernetes today. Our demos have used checkouts from, I don't know, 3-4 weeks ago. And with this, we're at the end of the presentation. Thank you, and happy to answer any questions you have.
I have one question on the, so this is transparent, right? So the application is not supposed to know it's being checkpointed and restored. How does it, are there any edge cases to that? So for example, how does it handle the fact that all the network connections are broken and then it comes up with a different IP address and stuff like that?
Yeah, so this is one of the most asked questions everybody has. And so the tool below, CRIU, handles TCP connections, so you can migrate a TCP connection from one host to another host. The thing is, you need to have the same IP address, which is pretty unlikely in a pod. We are able to recreate it in the demos by editing CNI files, or you can edit the checkpoint information to have the IP address of the new pod. But there's also the option, what we use in our demos, there's an option, we just say all open connections, we say are closed. And then the expectation is, of course, that the application handles automatic network reconnects.
So one of the problems with TCP connections is that essentially with CRIU, we have a locking mechanism that has to drop all incoming packets from clients, and this prevents sending the TCP reset packet to the client. But in Kubernetes, because the network namespace is allocated to pods, this mechanism, it doesn't work. Essentially, CRIU cannot apply this mechanism, and we checkpoint restore within the namespace. And as Adrian mentioned, there is CRIU provides a TCP close option, which can be added to a configuration file that essentially closes all TCP connection and then essentially reconnects after restore. And in general, it depends on the use case. So for live migration, it's important to checkpoint restore TCP connections, but for fault tolerance, where essentially you can restore the checkpoint a week later or something like this, then it's not that. Essentially, we use the TCP close mechanism.
Okay, thank you.
Do you see any kind of fundamental blocking points to get actual live migration, the way we are familiar with VMs transferring between nodes?
So at this point, it's, from my point of view, it's not a technical problem. It's finding the right way to integrate it in Kubernetes. It's kind of a feature that breaks a lot of assumptions because containers are stateless and things like this. So I think that's the hard part, finding the right way how to integrate it in Kubernetes without breaking any, I don't know, infrastructure assumptions from something. I don't know. That's, yeah.
So one of the problems with GPUs, I guess, for live migration is that you need to have the same GPU on both sides, and you need to have the same number of GPUs. So this is something that could be improved in the future, but in general, there are certain limitations. You need to have the same libraries, and yeah, there are certain requirements for live migration to work.
Yep. But I think those are the same with VMs. If you change your CPU or your GPU, then it's probably not going to work.
Hi. So follow up to the first question that you got. Can this be used for databases, like say you have a MySQL database running or a Redis cache running? How effective would this be for those?
So we checkpointed both. We have the Microsoft SQL database was checkpointed a couple of years ago and migrated, as well as Redis is an example we also often use. Yes, it works. I think the main problem is, like the first question, do these tools handle network reconnections automatically? So I guess this would be something the tools need to handle to make it work more easily in any environment. If they do that, then I would say, sure, it works.
And in terms of performing the operation itself, you almost need the tech checkpoint in both places. Is there a way to sync the checkpoints in both places at once?
I don't know. So we need to transfer it we don't need it in both places. We need it on the system where we want to restore it.
So you mean it has to be on the same node? What about a multi-node? As in, does it support pushing to object storage or NFS?
Yeah, so the way how we do migration is we convert the checkpoint image to an OCI image and push it to a registry, and then we can use it from any node, any kubelet. The thing is, this image was rather big, so if I would have converted it on the original system, pushed it to a registry, and then downloaded it on the other machine, then it would have just taken much longer because I have to. The registry is just slower than using rsync from one node to another node.